Welcome back. In this lecture, we will look at certain properties of semiconductors that are relevant to a photoelectrochemical system. This lecture might be elementary to some of you, but it's better that we all understand the concepts that are presented here so that the further discussion on photoelectrochemical system is possible. You've all seen from high school what is the difference between a metal, semiconductor, and insulator. You've been told that the metals are solids which do not have a band gap. Semiconductors have smaller band gap compared to the band gap of an insulator. It is useful to have some numbers in your mind so that what is small and large becomes clear. The way to think about what is small and large is with respect to kT at room temperatures. kT at room temperature is about 26 milli electron volt. So when you say small or large, we are always referring to kT is Boltzmann constant times temperature. This is the thermal energy available to all the molecular degrees of freedom. So when you have a semiconductor, the band gap of a semiconductor, the most common semiconductor is silicon. Silicon has a band gap of 1.1, and insulators will have a band gap of, let's say, about 6 electron volts. And 1 electron volt is approximately 100 kilojoules per mole. And a typical covalent bond has an energy of, let's say, 2 electron volts, and hydrogen bonds have energy of 0.1 electron volts. It's good to have these numbers in your mind so that you can get a better physical feel to what is being discussed. Let's move on. Let's also understand what we mean by a band. A band, here you are referring to a valence band and a conduction band. A band refers to closely spaced molecular orbitals. Again, this has some jargons. What exactly do you mean by an orbital? Orbital corresponds to a wave function for a single electron. A wave function is something that holds a single electron. Wave functions are obtained by solving the Schrodinger equation from quantum mechanics or quantum chemistry. We are not going to go into details of quantum chemistry, but these jargons have to be clarified. So orbitals refer to wave function for a single electrons. These orbitals, if they are present in a molecule, it's called a molecular orbital. And if they are present in an atom, they would be referred to as atomic orbital. A solid can be considered as a giant molecule. So an orbital that is present in a solid can be considered as a molecular orbital. And each orbital has a particular energy. Okay, so these energies are eigenvalues of an eigenvalue equation, that is the Schrodinger equation. If the energies are closely spaced, what do you mean by closely spaced? They are of the order of the spacing between different level is of the order of this energy. Okay, so here there is the energy is shown to increase, and all these a particular band has many different energy levels. They are all closely bunched together. Each of the orbital or each of the band in a solid can be correlated to a specific orbital in an atom. So how these orbitals give rise to a band, you might have seen this qualitatively in your high school. And that amount of understanding is good enough for the rest of the discussion. So just this set of concepts have to be connected. A band consists of closely spaced molecular orbitals. That is, the energy difference of each of the level is of the order of this value. Orbital refers to a wave function of a single electron. Each band can be correlated to an orbital in an atom. In a metal, there is no or negligible energy difference between a filled orbital and an unoccupied energy level. If this is the case, when you apply an electric field, typically application of an electric field involves excitation of the electron. If that is, the electron has to go from an occupied level to a higher energy level. And in a metal, this higher energy level is unoccupied. It is readily available for the electron to get excited from a filled level to an unoccupied level. However, in a semiconductor, if it is completely filled, if you excite an electron because of application of an electric field, just above the highest occupied molecular orbital, there are no unoccupied orbital. So there is a finite energy gap. Therefore, there is no unoccupied energy levels in this region. There is an energy gap. Okay. Overall, the important thing to understand is, if a band is completely filled, as this is the case here, or if it is completely empty, as is the case here, these bands do not allow for electronic conduction. That is, electrons cannot be easily transported if a band is completely filled or completely empty. So there is a particular quantity which is going to be referred to in subsequent lectures. It is the number of free electrons available in a material. Okay, so this will be given this symbol N. This is going to be an important feature when we are talking about the electronic properties of semiconductors. So if the number of free electrons is large, then the electronic conductivity is large. If N is small, the electronic conductivity is less. It is possible to excite an electron from a valence band to a conduction band. Any excitation is going to be temperature dependent. Just if a material is present at a non-zero temperature, depending upon the temperature, excitation is possible. If greater is the temperature of the material, greater is the excitation of an electron from the valence band to a conduction band. This object, which is schematically indicated here, is called a hole. A hole is an absence of an electron in a particular band. And this object is an electron that is present in a conduction band. These electrons are available for free movement in this band, and this hole is available for a free movement in the valence band. These are freely mobile carriers that allow for electronic conduction. We will understand what is intrinsic and extrinsic in the next two slides. So typically for now, intrinsic means we are referring to a semiconductor that is undoped. Okay, so for example, if you have silicon, a silicon which has not been doped is will be referred to as an intrinsic semiconductor, and corresponding to an intrinsic semiconductor, there is an amount of free electrons that are possible. These free electrons uh, will be dependent on temperature, and the number of free electrons in an intrinsic semiconductor will be denoted by this symbol N subscript I. The conductivity of a semiconductor increases with temperature. Why is that? That is because as the temperature increases, the excitation of electrons from the valence band to conduction band increases. With that, Ni increases, which increases the conductivity. This is very different from the behavior of a metal. In a metal, typically increase of temperature decreases the conductivity of a metal. Why so? Qualitatively, uh, the scattering of electrons from the atomic lattice increases, and as the scattering increases, the resistance increases and conductivity decreases. As the temperature increases, the host's lattice, that is the atomic lattice, the vibrations increase, which in turn increases the scattering of electrons from the atomic lattice. So when an excitation has occurred, de-excitation is possible. What do you mean by de-excitation? An electron from the conduction band can recombine with the hole in the valence band. This is called de-excitation or recombination. When recombination occurs, the concentration of free carriers decreases. The ease of de-excitation is characterized by what is called a carrier lifetime. All these concepts are elaborated in semiconductor science and engineering literature. So what we are trying to do here is to provide one slide introduction to concepts that are perhaps covered over many lectures in a course on semiconductor science and engineering. So, but this limited introduction is sufficient for discussion of photoelectrochemical system. Um, so all these lectures have to be viewed while reading these references, which have some additional information. But to understand all these things in detail, you should probably take a course in semiconductor science and engineering. So if the carrier lifetime is large, what it means is that the excitation can be stabilized for a longer time scale. That is good because these free electrons and holes are available for electronic conduction. So the carrier lifetime is of the order of microseconds in a defect-free semiconductor. So that is, if you have, let's say, a single crystalline silicon, then the carrier lifetime is of the order of microseconds. However, when you have defective semiconductors or oxide-based semiconductors, the carrier lifetime is much smaller. So because you want to increase the carrier lifetime, it is advantageous to have defect-free single crystalline semiconductors, which are hard to make. The material processing involved in making a defect-free semiconductor is rather challenging. That is why the cost of semiconductor devices is also rather high. The intrinsic conductivity of a defect-free semiconductor is rather small because the intrinsic carrier concentration, which is dependent on temperature, is rather small. But this is advantageous because you can modulate the conductivity of a semiconductor in a very controlled manner. This is done by doping a semiconductor. When uh, a semiconductor is doped, that semiconductor is referred to as an extrinsic semiconductor, or the conductivity associated with a doped semiconductor is referred to as the extrinsic conductivity. Let us take the most common example. A silicon is tetravalently doped, bonded. So when you dope silicon with an element that is on the right side of a silicon atom in the periodic table, in the periodic table, right side, let's say the dopant that is being considered is arsenic. Arsenic, because it is on the right side of silicon, it has one extra electron. This is called excess electron, which can easily be removed from arsenic and goes into the conduction band. So here, few information is schematically presented. These are holes in the valence band. These holes have been generated because of thermal excitation. Corresponding to one hole, another electron is present in the conduction band. However, the number of electrons that are shown in the conduction band is much larger than the holes in the valence band. This is because these excess electrons in the conduction band are obtained not because of thermal excitation, but they are generated because of doping. This is called N-type doping. N-type doping goes towards increasing the number of free electrons that are present in the conduction band. Here, the conduction band is partially filled. Therefore, these electrons are readily available for transport of current in the conduction band. So there is another jargon. There is something called majority carriers. Here, in an N-type semiconductor, electrons are the majority carriers in the conduction band, and the minority carriers are the holes that are present in the valence band. As opposed to an N-type doping of a semiconductor, you can have P-type doping of a semiconductor. Let us take the case of silicon. If you take a dopant here, boron, which is to the left of silicon in the periodic table, so boron has one less electron, so it can readily accept an electron, and this acceptance of an electron by an acceptor dopant would give rise to holes in the semiconductor. So this is a P-type semiconductor. The best way to understand a P-type semiconductor is to contrast with an N-type semiconductor. So these electrons that are present in a P-type semiconductor, they are few in number because these electrons have been obtained by thermal excitation. Corresponding to thermal excitation, corresponding to these electrons, there are holes that are present in the valence band, but the number of holes that are present in the valence band is much larger than the number of electrons that are present in the conduction band, because these holes have been obtained not by thermal excitation, but because of acceptor doping in the semiconductor. Let us move on. the holes in the semiconductor are again characterized by number of holes per unit volume that is given as symbol P. Again, let us look into doping in some detail. When you have an N-type doping, let's say arsenic, we mentioned that arsenic has lost an electron, and this electron has gone into conduction band, right? Because it has lost an electron, it has become positively charged. So these immobile positive ions are called donor ions. Corresponding to each positively charged ion, there is an electron which is present in the conduction band. Likewise, in a p-type semiconductor, because the acceptor dopant has accepted an electron from the silicon lattice, it has become negatively charged, it is immobile. What is contributing to conduction are free mobile carriers. So the free mobile carriers are electrons in an N-type semiconductor that are present in the conduction band. And the free mobile carriers in an N-type semiconductor are the dominant carriers are the holes in the present in the valence band. The dominant carriers here are the majority carrier electrons in the conduction band. Here, the majority carriers are holes in the valence band. But what is important to understand is whether it is a p-type semiconductor or an n-type semiconductor, the doped semiconductors are net neutral. Corresponding to this positive charge, there is a electron. Corresponding to this negative charge, there is a hole. So the doped semiconductors are net neutral. Essentially, doping leads to availability of mobile carriers that contributes to conduction of current. It is possible to do electrochemistry with N and P-type semiconductors. So you may imagine that because electrons are present at a lot of electrons are present at higher energy, this N-type semiconductor can be utilized as a reductant for doing some electrochemical reaction. So electrons from a semiconductor, let's say electrons that are present in a conduction band, can be utilized, can be used for reducing an oxidant that is present in an aqueous solution, giving rise to a reduced species in the aqueous solution. Likewise, an N-type semiconductor, because it has holes in the valence band, and the holes like to accept electrons. So the holes can accept electrons from a reduced species that is present in the aqueous solution, and the species R will get oxidized to species O when the species R has lost an electron to a hole in a semiconductor. So this is an introduction how doped semiconductor can be utilized in electrochemistry. We will look into these concepts in greater detail as we progress in this lecture series. Typically, to ionize a donor atom, that is to separate the electron from the donor atom, it requires some thermal energy. This energy is small. Again, remember, when we say small or large, we are typically referring to 26 millielectron volts, because this is the KT at room temperature. So typically, one approximation that is utilized is all the dopant atoms are fully ionized. This is referred to as a full ionization dopant limit. So the if the concentration of the donor atom is denoted as Nd, it is the number of donor atoms per unit volume. If all the donor atoms are completely ionized, then the carrier concentration of electrons is approximately equal to the number of donor atoms. Why we are saying approximately? Because in addition to the electrons that you obtain from donor atoms, you would also have electrons due to thermal excitation from the valence band to the conduction band. So as a good approximation, N is equal to Nd. Likewise, in a p-type semiconductor, if all the acceptor atoms are been thermally excited, that is, there has been excitation from this level to the electronic levels that are present in an acceptor dopant, leading to the full excitation of acceptor atoms. In this case, Na refers to the number of acceptor atoms per unit volume, and a good approximation is the concentration of holes is approximately equal to the donor or the acceptor ion concentration in a p-type semiconductor. We'll move on to another important property in a semiconductor. Before moving on, please go and read these two Wikipedia links. These are concepts that you've been introduced in your high school literature, but perhaps it's good to revisit them. We're going to be using that in the subsequent lectures. So when you have, let's say, water molecule in, let's say, aqueous medium, water self-ionizes to go from this state to proton and hydroxyl. This requires some energy. But this state is possible at any finite temperature, and greater the temperature, more of this self-ionization is possible. Corresponding to this chemical equilibrium, you can associate an equilibrium constant. These refer to activity of protons, activity of hydroxyl, and activity of water. This equilibrium constant is dependent on temperature. And from here, you would have also seen what is called self-ionization constant of water. It is a constant at a particular temperature. It changes with temperature. The ionization constant depends upon the concentration of proton and concentration of hydroxyl. At standard temperatures and pressure, these two multiplied to 10 to the negative 14. So this relationship of pH plus pOH equal to 14 comes from this quantity being equal to 10 raised to negative 14. Why are we referring to all this? There is something called law of mass action in a semiconductor. This is usually the formula is given to you, but the basis for the law of mass action in a semiconductor, the underlying thermodynamic logic is very closely related to all the concepts that are stated in these two wiki links and self-ionization of water. So corresponding to a proton, in an analogous manner, the concentration of p-type carriers is like the proton carriers in water. Corresponding to hydroxyl, you can correlate the n-type carriers in a semiconductor. So Ni squared, that is the concentration of intrinsic, Ni refers to intrinsic carrier concentration. Ni squared is equal to P times N. This is often stated as a law, but the basis of the law is pretty much like what you have seen in simple chemical equilibrium in water. Stretching the analogy further, you can, like you had seen that the conductivity of pure water is very low, the electronic conductivity of pure silicon is also very low. One way to increase the conductivity of water is to dope it with an acid or a base. Doping water with an acid is similar to doping silicon p-type. Doping water or adding base to water is like doping water with base. That is like doping silicon with um, an donor atom, making it n-type. So what we are trying to do here is to not confuse you. What I'm trying to emphasize is when you try to understand a new concept, the new concept can be understood via analogies to things which you have already understood. Hopefully, from your high school, you have understood all these things, what you mean by self-ionization of water and so on. So based on these concepts, it is possible to rationalize how one may obtain this relationship. Even if you don't understand the basis of relationship, it is you're going to be just using this relationship, but it is not too difficult to get an intuitive understanding for this relationship that is presented in the context of semiconductors using the concepts that you have seen in your high school. Um, it is also useful to have some numbers because these numbers will be utilized in subsequent lectures. Typically, the intrinsic carrier concentration is of this quantity. Okay, it's about 10 to the 10 electrons or holes per unit centimeter cube. This is the intrinsic carrier concentration, let's say in silicon. When you dope it to a small extent, the carrier concentration is of this order. When you dope it, when you have a semiconductor that is doped to a greater extent, you have this carrier concentration. We'll be using these numbers in later lectures. As I mentioned, the dominant way of changing the resistivity or conductivity of a semiconductor is not via modulating the temperature. The dominant way of changing the resistivity is via doping, depending upon n-type semiconductor or p-type semiconductor. You increase the acceptor concentration or the donor concentration. When the concentration of acceptor ions or donor ions is increased, what you see is the resistivity is brought down. You can also see that the n-type semiconductors have a lower resistivity compared to p-type semiconductors. The basis for this difference is beyond the scope of this lectures, but it is an useful information that you may use in some subsequent lecture. What is also important to understand is it is useful to contrast the resistivity of semiconductors, even a doped semiconductor, with metals. Even when you dope the semiconductor, the resistivity of doped semiconductors is much more than the resistivity observed in common metals. Let's say copper, you have the resistivity in micro ohm centimeter. Here, it is much more, right? So you may ask, why do we want to be using semiconductors in electronics? The reason for this is semiconductors are critical to microelectronics, and it is critical to microelectronic devices called transistors. Transistors are as significant to modern civilization. Because they are so significant, they are often referred to as the wheel of the modern times. Okay, so we live in a silicon age, like you had Iron Age or Bronze Age or Stone Age. We live in a silicon age, and what is critical to transistor are semiconductors. So semiconductors are greatly utilized in the context of semiconductors, but in the context of transistors and the microelectronics. But we will also use and discuss semiconductors in the context of photoelectrochemical systems. In the next lecture, we will look at semiconductor energy scales that are relevant to photoelectrochemical systems. Thank you.